All right. So today we're going to be talking about momentum. You can see from these gifts right here, it's kind of giving you a little bit of a preview as to what it is that we're going to be talking about when it comes to momentum. Right. So, what is momentum? When you think about it in your everyday life, I'm pretty sure most of you all have heard this term. I like to watch sports. I think football is probably one of my favorite sports to watch. And I really, one of the cool things about it is like the contact, right? And a lot of that has to do with momentum, right? So how would you describe momentum in your own words? Just take a second to think about how you would define momentum. All right. So we are going to go into detail, right, into what momentum is, but these are some other things that we're going to learn. So by the time you're done with this lesson, you should be able to explain the concept of momentum and give examples. Should be able to calculate momentum using the formula. Be able to explain the law of conservation of momentum, be able to explain and give examples of collisions between objects. And this is where we'll get started, right? It's kind of defining what momentum is. So all moving objects have what Newton called a quantity of motion, right? This is what I was talking about is you see these movements every day. You are these movements every day, right? From whatever it is that you're doing, whether you're driving, whether you're walking, whether you're just kind of sitting there, right? There are some numbers that you can use to quantify the things that you were doing. And so this is what Newton is talking about, like giving things numbers, right? So this is kind of how you can trace back how people have traced back kind of like the Big Bang and the moving of the stars is using math, putting numbers to the movement of objects and being able to determine things, to calculate things because of being able to give them numbers, right? So quantity of motion. So this is what I was talking about, right? We are just giving numbers. We're giving properties to the movements that we do every day, and that's what we call momentum, right? And kind of a vague example. We're going to see a little bit more in detail what it is that I'm talking about, right? And you can see momentum is a characteristic of a moving object that is related to the mass. Remember this, y'all, because this is very important. The mass and the velocity of the object, right? So here you see just kind of a little review on speed and velocity. Speed is just simply how fast you are traveling, right? This car is traveling at a speed of 20 meters per second. Here, velocity is speed, but in a certain direction, right? This car is traveling at a velocity of 20 meters per second. And this is what makes it velocity is that they are adding a direction east, right? So momentum increases when either mass or velocity increase. And think about that football example, right? Think about the size of a football player and the speed of football players, right? They are both big and they are fast, right? So that is mass, that is velocity. But just keep that in mind as we go through this lesson. So a little bit more. I remember this formula, y'all. This is a formula for velocity. Kind of a little bit weird that they're using a P to represent momentum. But if you see here, there's already an M being used, right? So it'd be kind of confusing if you had two M's. So for this formula, remember that momentum is P and momentum is equal to mass times velocity, right? And just kind of envision that example of like the football player, how much momentum they have, their mass, basically how big they are. We can think about it that way, how big they are and how fast they are moving in a direction, right? So, and I'm going to be repeating myself quite a bit, y'all, but that's just for your benefit, right? The more I repeat something, the more likely it is to stick in your brain, right? So the momentum of an object can be determined by multiplying the object's mass and velocity, right? And keep whatever I keep talking about a football player, but if you like watching like racing or something like that, even like pool, if you like playing pool, it's objects kind of like colliding into each other, having to do with their mass and their velocity. So again, formula: momentum equals mass times velocity. And since mass is measured in kilograms and velocity is measured in meters per second, and think about that, right? This is how many meters something travels in a second. And the unit for momentum is kilograms times meters per second, right? So that is a unit for momentum. It's going to be this right here, kilograms times meters per second, right? And formula, yeah, just a P instead of an M. And remember that because there will be questions about what the P represents, which is momentum, what the M represents, which is mass, and what the velocity represents, which is this V right here. So keep that in mind. So, continuing on what is momentum, like velocity, acceleration and force, momentum is described by its direction as well as its quantity, right? So, you're definitely going to have to give a direction whenever you're talking about momentum. The momentum of an object is in the same direction as its velocity. And that kind of makes sense, right? Because if you're going one way in a certain speed, it makes sense that your momentum is going that same way, right? If you're traveling downhill, in one certain direction, and your velocity, right, you're picking up speed, it makes sense that that is the same way your momentum is going, right? So kind of weird because we just assume that's how it is, but there was some thought, right, some scientific thought put to these to these notions. And so the more momentum a moving object has, the harder it is to stop. And that makes sense, right? I remember when I was a kid one time going downhill. The hill was kind of steep, and I was kind of scared to do it. But I was like, yeah, you know what? Let me just do it. And I probably shouldn't have done it. The hill was so steep. I picked up so much speed going downhill that I couldn't stop the bike. Eventually, I just tried. I probably should have just, kept my momentum going, waited for the ground to level out and slow down. But instead, I tried to brake while I was like halfway down this hill, and because I was going so fast, when I tried to brake really hard, the bike just kind of like flipped over and I hit my head on the pavement. Right. So, a lesson that I remember well, having to do with momentum. Right. And then I was a big kid too. So, like, I definitely had my mass and my velocity going against me in this instance. And that's what you see right here, right? In this example, these kids more or less are the same size, but as you can see, the girl right here in the white is a little bit taller, a little bit bigger than this little boy right here, right? So they're kind of coming at the same velocity, so at the same speed, right? Different directions, are running towards each other. And so you see he flies back, and that probably has to do with the mass of this kid being a little bit bigger than this kid over here, right? And he just goes flying backwards. So, how do you think the mass of an object affects the amount of momentum the object has? Kind of already talked about that, right? Again, I like to repeat myself over and over just so it kind of sticks. But yeah, it kind of makes sense, right? That the mass of an object will affect the momentum something has. As an example, you see right here, you can catch a baseball moving at about 20 meters per second, right? But you cannot stop a car moving at the same speed. And why is that? The car has more momentum because it has greater mass, right? Again, it will be a lot harder to try to stop the moving car than a moving ball because of the mass. The mass of the car is huge compared to the mass of a baseball, right? So that again, remember, mass is part of the equation. Uh, Momentum equals mass times velocity, right? So we talked about mass. So now let's talk about the velocity, right? The velocity of an object also affects the amount of momentum an object has. And so, for example, an arrow shot from a bow has a large momentum because although it has a small mass, it travels at a high velocity, right? An arrow does not have a whole lot of mass. Think about it. It's kind of, it's a little bit long, but it just does not take up a lot of space, right? It doesn't have a lot of mass. Think about a bullet. Same thing with a bullet, right? It's not very, there's not a lot of mass to it. But the thing about these is they travel at a high velocity, right? And so because the velocity is so high, that gives them a lot of momentum. So much so that that arrow can pierce that metal, that chainmail, right? And this guy's pretty cool. He's an actor. I think he passed away a few years ago, but he was also the voice of the Army Man in Toy Story, and he was actually in the military himself. So he plays a lot of like military roles in movies, or he used to. So yeah, that has again mass and velocity have to do with determining the momentum, right? So think about this. An object's momentum depends on velocity and mass, right? We've been talking about that. So if both of these dogs have the same velocity, right? They're coming at you at the same speed pretty much. Which one has the greater momentum, right? So if you look at them right here, this little guy, if he came running at you at the same speed of this one and they jumped into your arms, you would probably be able to just catch this guy, no problem, pick him up in your arms. But if this bigger guy right here tried that, he would probably knock you on your butt, right? If you tried to stop him and like catch him in your arms while he's running at you full speed, his momentum is so much so that it's probably going to knock you on your butt because of its mass, right? Because of this dog's mass. And so remember, velocity and mass determine momentum. And so let's do this quick check. An object's momentum depends on blank and mass. So go ahead and pause this and answer the question. Right, so a velocity. An object's momentum depends on velocity and mass. Remember, P equals M times V. In the formula P equals M times V, what does P represent? P represents momentum, right? You would think it would be an M because of momentum M, but there's already an M in the formula. So in this case, P represents momentum. True or false? The momentum of an object is in the same direction as its velocity. This is true. Remember, if you're going downhill in a certain at a certain speed, it makes sense that your momentum is going downhill at that certain speed, right? It's not like you're all of a sudden going to just fly backwards when you're running downhill. So an arrow shot from a bow has a large momentum because it travels at a high velocity, right? Not a lot of mass to an arrow or a bullet for that matter, but they have so much momentum that they are pretty much unstoppable by a lot of different things because they are traveling at a high velocity. All right, so now let's look at the sample momentum problem here. Which has more momentum, a 3 kilogram sledgehammer swung at 1.5 meters per second or a 4.0 kilogram sledgehammer swung at 0.9 meters per second? Right, so down here again, we have the formula. And just remember, you're going to have to use this formula on each of these sledgehammers. And so I color coded these right here so that we could track what it is that we are looking at. So read and understand. Again, they're giving you two different sledgehammers and they want you to find the momentum for each one to see which one has more of it, right? Which one has more momentum. So what information are you given? So in yellow here, you see the 3.0 kilograms. That is the mass of the smaller sledgehammer, right? You know it's smaller because this one is 3 and this one is 4. So the mass of the smaller sledgehammer, you could just write it here to be 3.0 kilograms. The velocity of the smaller sledgehammer, they give that to you here. And I put that in the light green right here. And the velocity of the small sledgehammer is 1.5 meters per second. And we'll see this again on the next slide. So that's why I'm not actually like filling them in right here. And so the next piece of information, the mass of the large sledgehammer. That mass right here is 4.0 kilograms. And so that is what you would write right here. And then finally, the velocity of this large sledgehammer is 0.9 meters per second. Right, so you can see right here, visualize it again. There's a smaller sledgehammer, but it's being swung a little bit faster, 1.5 meters per second. Here, this larger one is being swung a little bit slower, which is 0.9 meters per second. Right, so, and again, you're going to have to do the formula for each one. And they give you mass for the smaller sledgehammer. They give you velocity for the smaller sledgehammer. They give you mass for this large sledgehammer, and they give you velocity for this large sledgehammer, right? So you should have all of the information you need to solve this problem. So what quantities are you trying to calculate? What we just talked about, right? The momentum of each sledgehammer. What formula contains the given quantities and the unknown quantity? So this is the formula, right? Momentum equals mass times velocity, P equals M times V. And so we perform the calculations, right? So this is what you do. You find the smaller sledgehammer and the larger sledgehammer. Which has more? So again, the problem just kind of written out again, and now let's solve this problem. So the formula, and again, a lot of repetition, right? So hopefully by now you have this formula memorized. The small sledgehammer is 3.0 kilograms times 1.5 meter per second, right? It is the mass right here, M, 3.0 kilograms, V, velocity, 1.5 meters per second. So the small sledgehammer, when you work it all out, it is giving you the momentum of the small sledgehammer, 4.5 kilograms times meter per second, right? So 4.5. Let's see the large sledgehammer. Just plug them all in, right? Plug in the values. Here you have this 4.0 kilograms from here because it's the mass of the large sledgehammer. The velocity right here, 0.9 meters per second. You plug that in right here, and then you just multiply them, right? Because when they're next to each other like this, the M and the V, that just means multiplication. So 4.0 times 0.9, that's going to give you 3.6 kilograms times meter per second. So which one of these has larger momentum? 4.5, right? So the small sledgehammer is larger than 3.6. And so even though it is smaller, y'all, the mass is smaller because it is being swung at a more of a higher velocity, like this GIF back here with I just like watching the watermelon shatter under the momentum of the hammer, right? Eventually the momentum is stopped by the table down here, but the watermelon does not do a good job of stopping the momentum. Right, but that is what you see right here is the momentum of that hammer swinging, and you can even see like the force that the table kind of vibrates once it's hit by the hammer. right? So in this case, the small sledgehammer has more momentum, right? 4.5 compared to 3.6. So here's another example. A golf ball travels at 16 meters per second while a baseball moves at 7 meters per second. The mass of the golf ball is 0.045 kilograms, and the mass of the baseball is 0.14 kilograms. Which has a greater momentum? All right, so let's just look at the problem and solve it this time. So we have the golf ball, we saw that, we have the baseball, and we want to know which one has a greater momentum. So let's go ahead and take the momentum of the golf ball first, right? Meters per second, this is going to be its velocity right here. And while a baseball, and let's see, so that's the velocity of the baseball. What is the mass of the baseball? So the mass of, or sorry, of the golf ball. The mass of the golf ball is 0.45, right? So mass is 0.045 times the velocity, 16. So what is that? 0.045 kilograms. Remember, the mass times velocity, m times v, is going to give us 0.72 kilograms times meter per second. So that is the momentum of the golf ball. So now let's find the mass of the baseball, which in this case, it is 0.14 kilograms. That's the mass. So mass times velocity. The velocity is 7 meters per second. So this number times this number, again, the mass times the velocity, 0.98 kilograms times meter per second. So which of the numbers is higher? The baseball's number is higher, right? 0.9 is definitely higher than 0.7. And so in this case, the baseball has a greater momentum. All right, so let's do another one. What is the momentum of a bird with a mass of 0.018 kilograms flying at 15 meters per second? Right, so for this one right here, again, just mass times velocity. The mass is 0.018 kilograms times the 15 meters per second. So that is 0.27 kilograms times meter per second. Right, so this is how you calculate momentum. All right, so now let's talk about the conservation of momentum. In everyday language, conservation means saving resources. You might conserve water or fossil fuels, for example, right? These are some of the things that you, when you think about conservation, like what you would conserve. The word conservation has a more specific meaning in physical science. So in physical science, conservation refers to the conditions before and after some event. Right. And when I think of this, I teach chemistry too, right? So I think of the conservation of matter, like when you something goes into a reaction, a chemical reaction, the same amount of atoms of a certain element that go into a reaction, that same amount has to come out at the other end of the reaction, right? Nothing disappears or nothing is created. It just kind of rearranges itself. But what goes in, the same amount of that substance comes out, right? And so that's what I think about when I think of conservation and science. And so we're going to see something similar here with momentum. All right, so let's kind of see some examples of conservation and define it a little bit more, conservation and momentum. So this is kind of like what I was saying. What goes into a chemical reaction, the same amount of that has to come out of the chemical reaction, right? So it's kind of similar to this. An amount that is conserved is the same amount after an event as it was before, right? So the total amount of momentum objects have is conserved when they collide. Right, so it's kind of what you see in that little GIF right here is that when it's hitting something, the momentum uh, is conserved. So there's the same amount of momentum, but it's just kind of like being transferred to another object. And kind of like pool two, right, is another example, something similar to that. Momentum may be transferred from one object to another, like you see here, but none is lost. Right. So again, kind of like that pool example, and I think there's an image of that a little bit later. Um, one object's momentum is transferred into another object, but it isn't lost. The fact is called the law of conservation of momentum. So again, the momentum isn't lost when the objects collide. It's just transferred from one object to the other, but the same amount of momentum is still there. Right? Yeah, and this is what I was talking about the GIF earlier, right? The momentum of one object when you hit the white ball, the cue ball, and you hit that hits the next ball, and that hits the next ball, right? The momentum is being transferred to those other objects. In this case, another pool ball. And so the law of conservation of momentum states that in the absence of outside forces, the total momentum of objects that interact does not change. Right. So this would be, and let me go on to this right here. The momentum of the first ball is transferred to the second ball and then to the third ball. right? So this again is a conservation of momentum where one ball, the momentum is hit into the other one and then the next one. And some of you may be saying like, well, that's not true. Like things will slow down. The momentum doesn't just keep going. Well, yeah, that can be explained through uh, and actually, I'll get to that in a second. The amount of momentum is the same before and after they interact, right? And so the total momentum of any group of objects remains the same or is conserved. And this is what I was talking about right here, unless outside forces act on the objects, right? So if you're thinking, and we go back to this example right here with the pool table, the pool balls, there is an outside force acting on this. And in this case, that is friction, right? The felt of the table of a pool table causes friction, right? So it isn't like it's not smooth. It's kind of like a carpet, right? Which causes some friction, which slows the ball down, right? So that momentum is not completely conserved because there is friction. There's also like gravity acting on the pool balls. So, it couldn't just keep going and going. If it was in space and there was no gravity or any barriers or any friction, then these things would just keep going and going and going. But again, on Earth, we do have some of these things that cause friction. And here you see the example right there, that table and then the covering of the phone, right, the case is causing friction, which slows that object down, right? But if that object were not there, it would just kind of like slide down. Or if it was something like ice, there would not be a lot of friction. But in this case, and in the case of the pool balls, that friction caused by gravity and the felt of the pool table is going to slow some of that down and and so not all the momentum will transfer because of friction or outside forces. So let's see some examples right here. We're going to see a few different types of collisions here. This collision is with two moving objects, right? So if we just kind of look right here, and let me actually bring this right here. In the figure, a train car travels at 4 meters per second down the same track as another train car traveling at only 2 meters per second, right? So one of them is going a little bit faster, 4 meters per second. One of them is going slower, right? This one right here is the one moving faster, 4 meters per second. This green one is going 2 meters per second, but they're traveling in the same direction on the same track, right? So it makes sense that this one, because it's going faster and it's about to catch up with this slower one, they are eventually going to collide, right? Because right here, before the collision, the blue car moves faster than the green car, right? 4 compared to 2 meters per second. Afterward, the green car moves faster, the total momentum stays the same, right? So right here, you had 4 meters per second, 2 meters per second. Altogether, it adds up to 6 meters per second, right? So what you're going to see here, though, after the collision, though, you see right here, the momentum is transferred over to this other object. And now this object is moving faster. This one is going 4 meters per second, and this one ends up slowing down to 2 meters per second, right? So when there are two objects like this, in this case, the two train cars have equal masses. The blue car catches up with the green car and bumps into it. During the collision, the speed of each car changes, right? So the collision is right here, indicated by this little this illustration right here, and then you can see what was going 4 meters per second. Now it is going 2 meters per second, right? And this guy was going 2 meters per second. Now it's going 4 meters per second. So basically, the momentum of this blue car when they collided transferred over to this green car. And so the blue car slows down to 2 meters per second. That's kind of what I was saying right now. And the green car speeds up. So it's still the same example, right? And the green car, again, was going 2, and now it's going 4. The blue one was going 4, and now it's going 2, which means it transferred this momentum over here to the green car, right? The momentum is conserved. The momentum of one train car decreases while the momentum of the other increases. And again, there are other forces that are going to act on it, like gravity or the tracks themselves. But for the most part, this is what the law of conservation is saying when there are collisions with two moving objects. Remember that it transfers the momentum over to the other object when there are two moving objects. All right. So these are collisions with one moving object, right? So in this other one, they were both moving, right? The blue car and the green car. One was going 4 meters per second, the other one 2 meters per second, but they were both moving. In this example right here, you see one of them is going 4 meters per second, and the other one is not moving at all, right? It is just 0 meters per second. So the blue car is traveling, again, what I said, 4 meters per second. The green car is not moving. Eventually, the blue car hits the green car. After the collision, the blue car is no longer moving, right? But the green car travels at 4 meters per second. So you see again, we're talking about conservation of momentum, right? It's whatever you start with. So the numbers that you have, in this case, it's just 4 meters per second, right? And this one is 0 meters per second. But right here, after they collide, right there, you see that now all the momentum has passed because this one was completely standing still and this one was moving. But after they collide, the momentum goes from this blue car to this one right here, which is now going to 4 meters per second. So again, you start with 4 meters per second, you end with 4 meters per second. That is conservation, right? What you start with is what you end with. Same thing in this example right here. You start with 6 meters per second altogether, right? 4 and 2 is 6. Right here, when you end, it transferred it over, but you still have 2 here, 4 here. So it's still 6, right? So you start with 6, you end with 6. This one, you start with 4, you end with 4. Even though the situation has changed, momentum is conserved, right? Started with 4, you end with 4. All of the momentum has been transferred from the blue car to the green car. All right. So the first one was when two objects were moving. The second one was when one was moving and the other one was not. This is when collisions with connected objects, right? So in this case right here, you see they are moving. They're not connected right here when they start off, right? And so let's go with this. The velocity of the coupled trains is 2 meters per second, half the initial velocity of the blue car, right? So right here, if the two cars couple together, momentum is still conserved. Together, the cars move slower than the blue car did before the collision, right? So right here, you see they are connecting. And so right there, they're not connected. This one is moving, this one is not. But what happens when they are connected like this, right? So since the mass is doubled and the velocity is divided in half, the total momentum remains the same, right? A little bit confusing to understand, but the main thing to take away from this is what you start off with is what you're going to end up with, right? So you start with 4 meters per second. What you end up with is 2 meters per second plus 2 meters per second. It's still 4, right? 4 meters per second. So again, you are conserving the momentum. Whatever you start off with, whether it's the two objects moving, one is not, or this one where they're connecting with each other right here, you see they connect. This right here is a conservation of momentum. And so suppose that instead of bouncing off each other, which is what we had seen in the other ones, the two train cars coupled together when they hit, is momentum still conserved in figure C? Yes, right? It's what we were saying. After the collision, the coupled train cars make one object with twice the mass. So now instead of being two different objects, they are one object, but they are still carrying that momentum of 4 meters per second, right? 4 meters per second, 2 and 2 makes 4.